Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 25. It's on covalent network solids, which are solids made of these vast networks of interconnected atoms, and those connections are made with covalent bonds. Now, what's interesting is the three-dimensional structure tells us a lot about the properties. And so a great example would be this: diamond and graphite. In other words, graphite that you write with a pencil are made of the same thing. They're just made of elemental carbon. But depending on how those carbon atoms are hooked together, we can have one of the hardest things on our planet, a diamond, or we can have something that is going to be broken by the paper that you're writing on. And so covalent network solids are made up of either one nonmetal or two nonmetals. So an example of one nonmetal could be graphite or silicon that we use to make computer chips. An example of two nonmetals might be silicon oxide that's going to make up quartz or silicon dioxide. Generally, these covalent network solids are made from the carbon group. And the reason why is that they have 4 valence electrons, and it allows them to make all of these vast number of bonds. Their structure can either be two-dimensional, so graphite will have these two-dimensional sheets, or it can be these vast three-dimensional lattices. And depending on what kind of structure they have, it's going to give them different properties. So for example, graphite is going to be incredibly soft. That's because it's going to have these soft layers, but it's going to have a high melting point because you're going to have these covalent bonds. Silicon is going to have a pretty good structure. It's going to have a higher melting point, but as we increase the temperature, we start to vibrate those atoms, and it can actually become a conductor. So it's something we call a semiconductor, and so we can vary the amount of electricity that is conducted through it. And one ways we can do this is we can dope it. We can add different elements to it, different other atoms. We can either N-type or P-type dope it, and we can add either electrons or the lack of electrons. And so it allows us to create things like transistors. And so this is an example of a covalent network. This is silicon dioxide. These are the crystals in quartz, and you can see that it has this regular structure. Now, the picture that I'm showing you right here doesn't show that three-dimensional structure. We're just looking at one layer. But in general, they'll form these massive crystals. And so you can't really say that it's a molecule per se, because it's going to be more of a ratio of all the atoms that we have in this giant network. It's almost like an ionic solid in that sense. They're going to be made from the carbon group, and so carbon, silicon, germanium. And the reason why, remember, is they have 4 valence electrons, so you can make these vast connections. They could have a two-dimensional shape or three-dimensional, and as a result of all the covalent bonding, they're going to have a really high melting point. So here's a picture of graphite. This is what it looks like if we were to zoom down to the level of the atoms, and what you see is that there are going to be covalent bonds that are connecting all the carbon in each of these different layers of graphite. But what's missing is that 4th bond. In other words, I can only see 1, 2, 3 bonds to each of those carbons. That means that there are free electrons, and what those electrons are going to do are interacting with electrons from the next layer. And so you get these London dispersion forces that are holding those layers together. And so those are going to be relatively weak, and so it's easy for these layers to slide past one another. And that's why we could make pencil lead out of graphite. Silicon is going to have a much more regular kind of a three-dimensional shape, this diamond lattice. And what's amazing, this is what silicon would look like if we could model it. You can see that there are 4 bonds now around each of those silicon. What we get is one massive crystal of silicon. That's all it is silicon in here. And what we can do is we can cut chips out of this. And so we can make the chips that are in your phone or in your computer. And so what's interesting about it is as we increase the temperature, we increase conductivity. So as we make it hotter, more electrons can flow through it. Now, that's not the only way that we can regulate the amount of electron flow. We can also dope it. And what does doping mean? Well, if you look right here, we've got carbon and silicon, so they're each going to have 4 valence electrons. But what we can do is we can take atoms from the next group or the group below it, and we can either increase the number of electrons or decrease. And so let me show you what that looks like. We could dope it with phosphorus. That's called N-type doping. And the reason it's N-type doping is now phosphorus fits right into the lattice. It's going to bond to these 1, 2, 3, 4 atoms around it, but it's going to bring with it an extra electron. And the reason we call it N-type doping is it's increasing the negative charge that's going to be in that silicon. So it's easier for that to flow. So let me put that back for a second. We could also grab boron. So if we grab boron, it's going to have 3 valence electrons. It's going to bond to these 3 atoms around it, but it's going to bring with it a lack of an electron. And in electronics, we call that a hole. And so that's a lack of an electron, and it's an area where electrons could flow into that. And really, they talk about the holes actually moving around. And so p-type doping stands for this positive or a lack of that negative charge. And so where would we ever apply this? One of the greatest inventions of the 20th century is the transistor. And I'll put a link down below to a Veritasium video that explains how transistors work. It's totally fascinating. But the three parts of any transistor, they used to be much bigger than they are today. There are going to be three leads that go to it. And so essentially you're going to have a source where electricity can flow in, a drain where electricity can flow out, and then we're going to have a gate. And what you have is N-type on either side. So this is N-type silicon on either side, and then you're going to have P-type in the middle. And there's going to be no electrical flow. And so what we can do is we can add a little bit of voltage at the gate, and what you get is now electrons are able to flow. So we've got all these excess electrons here, flows through the holes, out the drain on the other side. And so what's amazing is we can make these things incredibly small. We call them solid state transistors because they're made of solids. And so on a typical integrated circuit like you might have in a computer, there might be billions of transistors just on that one circuit. And so this is just application of that covalent network solid. So did you learn the following? To create a covalent network solid representation, remember it's going to be these three-dimensional lattices of either one or two elements, non-metals. And then could you relate that structure to its properties? Remember, if it's two-dimensional, if they're not connected, it's going to be really soft. If it's three-dimensional, it's going to be really rigid. And also, since there's covalent bonds in here, they're going to have a high melting point, and I hope that was helpful.